Yes, so today I'm continuing with reading and writing files. Last time I finished with how to write to screen, so the natural follow-up is how to write to disk. There are, just like in Python, you must connect identifier to a file name, and that you do with the open statement. And in this open statement, you also determine if you should read and write the file. There are three modes of operations of files. You have text I/O, that's just like we did in Python. Name list I/O, which is text files with name variables, so it's similar to the JSON but with its own format. You also have binary files that is called unformatted I/O. Just like in Python, when the file I/O is completed, the files needs to be closed, and you do that explicitly with a close statement. And there is no automatic way of doing this, so you need to make sure that you always close your files. Otherwise, it could be that you lose data when the application closes. So this is a way you can do it in Fortran. So what I usually do is I declare my file identifiers as constants in the program. So instead of using numbers like they are, we use the constant identifier instead. So in this case, I have in file and out file. Give them different numbers here. Then you open here, and then you give certain number of parameters. So you have the first parameter, unit, is the file number, and I just give it a constant here. Then you have to associate that file identifier with a unit with a file name. So the second parameter. Then you have to tell it what kind of mode you want to access the file. And access equal to sequential, that is text file based. And then the final parameter is what operation you want to do. So read, in this case, I want to read from the file. Reading from the file is you use the read statement. And the first parameter of the read statement is the unit from where you want to read. The second one is the format, or how you want to read data, but in this case we leave it as a star, then it reads everything, and then you give the variables that you want to read in. And here, Fortran, opposite to Python, it can handle different different data types. So if you read an integer, there's text-based integer in the file, it will convert that to an integer. So you don't have to do any conversions. You will probably get errors if it can't convert, but it handles that automatically. And then finally, you close the in file. And then the same thing here, if you open for writing, you do unit, out file, sequential, but the difference is that you put action equals to write here. And then you use the write statement with a unit out file here, and then the star here, because we don't specify the format. And then it will write those to disk with the highest precisions possible. But they will still be text-based. And then finally you close the file again. Reading from keyboard. So there are unit files that you need to specify that has special meaning. So in this case here, 5 here is the hard-coded since forever back in time is number 5. And that is equivalent to star here. If you put that, then you don't have that will be number 5 here. And then reading is the same thing here with unit IR instead here. Here you can see also that number 6, that is writing to a screen or standard output. Same thing, have a star here, that means the same thing, but 6 has a special meaning, so don't assign them and open them as file. Those are reserved units that you shouldn't use. So, code structuring. So when you have a larger program, you need to kind of do things in different orders. You have to group them together in a way that you can maintain the code as well. And if you just have a single file that does a very specific thing, it's probably not necessary to modularize it. But usually applications, they grow and they become larger and larger. And sometimes you need to get in do something to be able to maintain the code. But just as in Python, in modern Fortran, the key to modularization is the module. So Fortran also has a module system, and modules can be used to group related subroutines and data together in a logical way. So you can, in module, you can define both variables, parameters, and subroutines. So they go together in a module. And this is one way of thinking of it. You have a program, and instead of putting everything in your main routine or in a main program, you can divide it up into several logical modules. So in input data, I have everything that handles loading the module, defining the data. I have an output data module that handles the writing of the output data during the simulation, for example. I have a finite element module for defining those functions. I have a solver module. And then at some point, I also have miscellaneous routines that I don't know what to put, but kind of utility routines that I use in many programs. I put them in the utils module. So all of these 4 modules uses the utils module here. The same thing with the program that uses those other modules. And in code, it can look something like this. So my stress-based simulation program here uses input data, output data, fem, and solve. And when you do that, all of these, the methods and subroutines for those modules will be available to your program, so you can call them. And then you can see here in module 5, I have use utils. So I don't use utils in program, so program will not see the functions in utils, but the finite element module will see all the functions in the utils subroutine. And also, if you use utils here, it's only module 5 that will get the access to the subroutines in utils. A little bit more subroutines. So this is a more advanced topics again, but in Python, everything is an object, and you can pass everything as an object. So a function is also an object, so you can very easily pass functions to other functions. You can do that in Fortran as well, but it's a little bit more complicated. The only thing that you need to kind of define is that the function that you pass must be defined as a type, and so that the subroutine knows how to call that function. And what you do that, you declare that in the specification part of your subroutine. So here's an example here. I have a module utils here that contains a function here. And then I have here inside my subroutine, I declare what the function here that comes in, how it's defined. So this is the interface of the function. It must look like this. And so it must be able to have the same, this function here, if you want to use this, it must fulfill this interface declaration here. The easiest way of doing this is put everything in a module and then have the function that you want to call inside here, and then you have the subroutine that you call the function in the same routine. And then you can use, so I use utils here, and then I can provide my function as an argument here. But they must, this is the requirement. So the compiler will check that this one here fulfills this part here. Otherwise it won't link. So this way you can do the same thing as we did in Python. You can pass a function that you want to plot over. A little bit more complicated, but not too complicated. Another cool thing that you can do with subroutines in Fortran is that you can actually have optional keywords. So that is something that was not possible before, and it's something that you can do in Python as well. But here you have to declare the parameter coming in as with an additional attribute here, optional. And then you can also check in your subroutine if the variable, the attribute has been, the variable has been defined as well. So there is the special function called present in which you can use to check this. So in this case here, I have a ice cream order subroutine, and I have, so number here, this is not an optional. The other two parameters, flavor and topping, are optional parameters, so you don't have to give them when you call them. So you can call this routine in all of these combinations here. This is the minimum, so you always have to provide 2 because number is not optional. You can do them in order, then it will, 1 here will be the flavor, 442 here, 2 here will be the topping. If you don't want to give flavor, you need to use keyword arguments. Otherwise, it doesn't understand the ordering. But all of these are quite legal. So this is very Pythonic in its way. So it's a really nice thing. And then you can see here, you can use if present flavor, then do something. If present topping, then do something else. So in this way, you can check what the user has provided to argument, and you can use, for example, default arguments here. So in Python, you can do this by setting default values on the incoming arguments, and then you don't have to give them. In this case, you actually need to know that, okay, it's not present, then I use something that is default. Another cool thing with subroutines is that you can do overloading. And what does that mean? Is that you can a procedure can be called depending on the data type. So you can have a procedure with the same name that you can use with multiple data types. And in Python, this is kind of obvious. You can do that all the time. But in Fortran, which is a typed language, you need to kind of handle this, how that should be done. So you can do this separately, but I will always recommend people to use modules for every more advanced features. Put everything in modules. That makes our life much more easy. So in this case here, I have a module called special, and I want to have a function that is to handle integers and one function to handle real, but I want them to be called func. So a user should be able to call, regardless of data type, the same name. And what you do then is in your module heading here, the section before the contains part, you put interface function, and then you say module procedure, and then which function to implement this function. In this case, I do ifunc, rfunc, and the compiler will select the appropriate one depending on the data types. So in this case, you can see I have integer function, ifunc, have integer here, real function, rfunc here. And this will be, A is an integer, then it will call ifunc. If B is a floating point here, then it will call rfunc. So it's a really nice way you can implement a generic library in Fortran to kind of select what type the function to call depending on the type. So that's nice. Another cool thing is that you can also do operator overloading, which usually is something that you do in more object-oriented languages. But here you can actually define operations on derived types. So if you have, for example, a vector, you can define vector and matrix operations using operator overloading, which is really cool. So you have an interface operator parenthesis, and then in the parentheses you can give the plus minus multiply, and so in this interface, and redeclare how it should be implemented. Usually the function has the form of your derived data type, function name, operand 1, operand 2. So here I have implemented a simple vector library with only one operation. So I have interface operator plus, and you can see here I declare my vector here as a real and with 3 components. And then I define I want the plus operator to be overridden, and then I give vector plus vector. And then you can see here I have type vector here, that is the data type I've defined, and I function vector plus vector, which I've given here for implementing the plus operator, 2 operands here, and then I do my vector addition here, and that's what you actually need. And then you can define vectors like this. And then you can do this. And that will actually call this routine vector plus vector. I think this makes the Fortran a much more nice scientific language as well, because you get all these these features that makes it more Pythonic in a way. Another thing you can do with modules is that you can actually limit the visibility of things in your module. So sometimes you implement the solver module that has a lot of state variables, but you don't want to expose them to the user. You can hide them. So you can give attributes that say this is a private subroutine, this is a private attribute. By default, everything is public. So you don't. If you want everything to be public, you don't have to do anything. It's just that if you want something to be private, you have to take action. So here you can see here I have a module. My module have integer public, so you can give them as attributes to the declarations. So visible is visible and private invisible. You can also do it with functions in the module. So the private function here will not be available to any of the programs or modules using this module. And the public function will be available. And the public function can call a private routine inside the module. So modules can use, for example, you can have a lot of helper functions in the module that you don't want to be part of your public API for the module. And then you can use these attributes to hide them. And then you can see here that I just compiled the program here, and I try to call the private function from this module. And you can see here it fails in when I link. So it can't even link the program together if it's private, because it's not visible. Pointers is, you don't have to deal with it too much, you just have to know that you can use pointers in Fortran as well. And in C, that is a very dangerous concept, but in Fortran, it's a very controlled way of using pointers. So I will show you. The pointer is a reference to a variable, so it's very similar to having in Python that you reference different things, but it's strictly typed, and things that you can point to must have a target attribute. So you must kind of dedicate this variable will be pointed to. And what you can do with this, for example, you can enable the return of allocatable arrays from procedures. It's actually something that in modern Fortran, if you have a recent Fortran standard, that is also not necessarily required. But what you can also do is you can implement data structure, derived data types that have, for example, a linked list or similar data structure in Fortran, which was a bit complicated before. Use zero or pointer using the nullify function, and that will disconnect the pointer relationship from the target. Operator is the equal greater than is the operator to associate the pointer with the target. So you don't use an equal to do this. So here I have several arrays. I have an allocatable array A. I have also two pointer data types. So you can see here that these are strictly typed variables. So integer dimension : so B and C are arrays, a pointer to arrays of two dimensions. Here I allocate A, and then I can say B should point to A. Now you can see here A has a target, so you can point to it. I can assign it like this. And now B works just like any array in Python, well, in Fortran. I have a create array here. This is a special function here. I have a D here that is an integer dimension pointer D. And here you can see I can allocate the D array inside my subroutine. And because it's a pointer here, now it's your responsibility to take care of it. So you can see create array C, and C here is a pointer, and now it actually has been allocated inside a subroutine. In the first standard in Fortran, you couldn't do this. This was kind of, so this is a relatively recent thing. It's just 20 years old or something. Anyway, it's a very nice feature. And then you can use C just like anything else here. So you can see this as a, so for example, if you have a library where you have some data structure that you want to kind of initialize in a certain way, in this way you can combine both the allocation and the initialization in the same subroutine. So the user can just call create array, and then it will get an allocated array. Of course, you have the responsibility to be able to deallocate C as well. So that's your responsibility. You can do B assigned to null, then that is the same thing as doing nullify B. So null is a special function that returns you a null pointer. However, now B is undefined. So if you do this, you get an old error box in Windows XP here, access violation. So in this case, you actually, it will not prevent you doing this, but it will crash a program. So be aware when you do the reference a pointer, you can still use it, but it will be a bit dangerous. So you have type pointers, and every pointer must have the things that you point to must have a target attribute, otherwise it doesn't work. Yeah, so what you can use this for is to implement more advanced data types in Fortran, like linked list, hash maps, binary trees, where you, in your data structures, have pointers to other data structures. Yeah, as I said, pointers, you can have a pointer in a derived data type. So in a linked list, you typically have a data structure with the data and a pointer to the next or previous entities. So that's where you can use it. That was kind of hard to do before. Before you had to have an array, and then you have an array of items, and then you use indexes to point to things. But now you can use the same structure that you have in other languages that you can point to data in memory. Advanced I/O, it's not that advanced. It's more advanced than I showed before. So list-directed I/O. And Fortran uses a special format for reading and writing variables to files. As I said before, you don't have to do text conversions yourself. Fortran will read the text file and convert the numbers automatically. Complex numbers has to have a parenthesis in the file, and strings must be enclosed with single quotes or double quotes when you do an output, and reading variables require the same format. So for example here, if I write a file, I do AB string topping C, you can see here that I have the numbers is output in a certain way here, and then you can see I have a logical, I think, as well here. Yes, the topping here, that F here, that is a true. So, oh, sorry, that is false, that's a logical, and T is true. But then you can see I have a complex variable here as well. And reading that back is no problem. It can read this, but you need to kind of put these things here in the output to be able to read strings. And then you just read them, and it will automatically convert to an integer, floating point, string, boolean, and a complex. It's nice. You don't have to think too much about, like in Python, you always read strings from files, and then you have to convert the strings to something. Fortran will handle that. Then we have something very similar to JSON, but it's more long time ago. But you can actually read and write lists of named values. And what you have to do then, you have to create something called a name list, where you give the names that you want to use in that file, so that the compiler can generate code that can recognize the variables in your file and assign them to a name list. And it looks like this. You have name equals to value, comma name equals to value slash. You can have arrays as well. Name equals to 1, 2, 3, 4, and 5. So it's harder to read than JSON, but it's very similar that you have this dictionaries of keys and values to read. So here we have a named list IO example. I have my variables here, number of eggs, liters of milk, kilos of butter. Then I create a named list called food. And I give the variables I want to be able to use in the name list here when I write. And then you can see here that I can just do read named list food. And then I will read from the file and use these and assign these variables automatically from the things that are in the file. Same thing here, you can write name list food. And I will write all those variables to disk. It's kind of a quick way of doing it. The final thing that I want to we can write is you can write binary files. Sometimes it's when you're using, for example, floating point variables, you actually don't always want them to go via a text file. For example, if you want to do snapshotting in your code, you could take variables and write them down in binary form and then read them back again with exact representation in memory. And then you can do using binary files. What you do then is you use read and write statement without the format parameter, and then you just write the variables down the disk. What you should think a bit about is that there is no kind of standard way of storing binaries in Fortran. So when you're writing on x86, you will get something that is for that specific platform. If there is some other processor architecture, it could be that the format is different. It's not so much anymore because most vendors or processors today have kind of standardized on the floating point formats, but there is nothing in the standard that says what is coming out from this. And typically uses scratch files, temporary files, snapshot files when you're writing your code. Or when you want to snapshot your simulation code at some point. You can write all the variables to disk. Yes, there is also there is something also called direct access files. So those are combined with the binary files as well. So in this case, if you have a structure like a database, you have names written with the name, telephone number, and so on, and you have a structure, and you have fixed record lengths. You can use direct access files to jump randomly in a file, and then you can go to any record randomly, and also you can change records. We're going to read back to files. You can also, before you write, you need to query how big is your data. So if you have defined your derived data type that you want to store, you need to query the length of that, because it could be that it's system dependent. Then you can use the inquire function to actually get the length of that. So here's an example again. I have a account data structure here that I want to have several records on disk. I have a balance here. Now I just define two, account A and account B, where this is a small example. I define a variable called record size that will store the length of the record here. So I do inquire, IO length, record size, account A. So here I ask how big is this? Then it assigns record size to the size of account A. I print it out here, assign my variables here, and then I write my data here. So record 1, account 1, record 2, account B. So this is the location in the file where to store your records. So this is how to write them. So when you want to read files again, you need to kind of be able to position yourself in the file. And there is an invisible file pointer or cursor in the file which you can use to jump back and forth. And you can use the functions here. Backspace, that moves the pointer one back. Rewind will go to the beginning. And then you also have end file, you go to the end of the file. And then you use the same thing here. You read back using the read statement here again. I think there are some more examples in my book online as well. So in Fortran we don't have any try except routines. So to handle errors in files, you need to add some extra parameters to your function calls. And if you have well-behaved programs to write them, you should make sure that you always check the error status. So in this case here, this is one of the exceptions that you actually use line numbers. So in this case, you can see here that error 99 here, that determines where to jump when you have an error in your file operations. Now you can see here you can provide this attribute here multiple times in every operation, and it will go to this line here, and then here you have to handle your error. So you can have multiple numbers here to handle different kinds of errors here. But this is the way how you do it. And not the most nice way, but that's how it is sometimes. So you can see that this is kind of the exception handling. In exception, you also jump to a certain point. And the same thing here. The exception is the error here, and it jumps to 99 when an exception occurs in the open statement. Yes. So Fortran has many new tricks. So I'll just go through them briefly here to kind of show you what you can do. Yes, there is something I showed you before that you can pass allocatable arrays using pointers, but in the recent Fortran standard that requirement has been removed. So you can use allocatable arrays as dummy arguments. So here you can see here that I can declare A here in my create array. The thing I do to enable this is the real allocatable intent out. Then I tell the compiler this is a variable that you will return from this function. If you don't do this, it will deallocate that variable automatically. So if you want it to go out, you need to do this intent out A. But then you can do create array here, and then you can use it. So before you had to use pointers to do this, but now you can do this without using pointers, which I think is really nice. And you can also do it for return values and functions. So you can actually create a really nice factory method here that returns an allocated array. So you can see here allocate create vector, and you can see here that I have this here dimension, a single one-dimensional array that is the data type of my function here. This was something that I showed in my classes for several years, and it was not implemented in most of the compilers, but now it works. Also, you can have allocatable arrays inside derived data type. That is also something was added later. You need to deallocate. So if you create derived data types and you have a lot of them in this, you're still responsible. There is no automatic deallocation here. So you need to, before you dispose of your large array of stack objects, you need to call the deallocate on the contents inside. Submodules. This is something that has also been added in response to you want to implement a single module with a lot of stuff in it. And the problem is that you get a really large source code file that is hard to maintain. What you can do then is you can divide implementation between multiple source code files and define them as submodules to a larger module. So here you can have, for example, submodule points that implements a certain feature of the big module points. So in this way you can separate out the implementation in several files and compile them separately. But they still will have a single interface to the user. C interoperability sounds like it should be easy because you have, for example, GCC compiler with a C compiler and a Fortran compiler, but actually the standards haven't had clear definitions on the data types. And that is something that has been added also in Fortran. There is a module called ISO C binding. If you use that, you will get all the C data types available to you. So then you can actually declare the exact data type in C in Fortran. And that is actually makes your life much easier if you want to link C and Fortran programs together. So here you can see I use the ISO C binding here in the top. I have declare, and now I can declare my variables integer C int. And now that corresponds exactly to a C integer, C float, C double, and so on. You have to have, if you want to declare them as you can use them as suffixes here in your data declaration as well. Really nice module. Another thing is that by default, Fortran always passes all argument or variables to functions as references. That is, even if you pass a scalar, it's actually a reference to the scalar in the calling routine. So if you modify that, there is always a side effect. And that is a problem because in C, scalars are passed by value. So it's not obvious how you can link a C routine to a Fortran code because the calls are not matching. And what you can do now in Fortran is you can actually, there is an attribute called value that you can declare in your subroutine that will make the dummy argument passed by copy using the same declaration as in C. I don't have an example here, but it makes it easier to actually link Fortran and C codes together. It also makes calling a Fortran routine from C much easier as well, because they have the same calling conventions. Another thing that has been added, which I was surprised when I first heard it, that there was no way standard-wise to get environment variables in Fortran, the Fortran language. So now you have get environment variable that you can query any variable in the system that's in your process. Command argument count. Command line argument for Fortran wasn't a thing. Most of the old Fortran codes communicated with standard input and standard output. But with this, you can actually use normal command line arguments as well. So you have the number of arguments. You can get a specific argument here as well. So let's see where we are. So now I've covered most of the Fortran language, so I will go through some tools that can be useful if you're developing Fortran code, how to handle, implement your project. So the first thing here is maintaining Fortran code. So when you have one or two files, you can do the compilations yourself. It's easy. You just call gfortran and give it the source code file, and you get the binary. But if you have a larger project and you're perhaps starting to get hundreds of files, and you update certain files, you want a way of handling the build of the program as well. And it could also be that you want to build your application for Windows, Mac, or Linux, and then you want to be able to have the same kind of build system on all platforms, so you don't have to do specific things for different platforms. You can do that with using shell script, but the problem is with the shell script on Windows, the default shell is not bash. So that kind of falls down. Also, when you have scripts, usually if you change something, you have to rebuild everything because it just loops through all the compilation. But there are some tools here that I will go through here, and that is make and CMake, and these can solve some of these problems or most of these problems for you. So I will go through make, and that is the underlying tool that will also be used in CMake. So those are kind of related but different. So make is a tool. You can type make if you have a Linux machine or you have a Mac machine. Usually you can type make, and it will do something. It's a command line tool that you can use to build software. And the idea is that it builds software from a set of rules. So you define how things are related in your project. So for example, if you're an executable, it depends on object files. The object files depends on source code files. And you set up those dependencies in the make file. And the nice thing with this, it will look at the file. So if it sees that a source code file has been changed, it knows also that, okay, now I have to rebuild certain things. And it only rebuilds the things that it is required to rebuild. And this is available on all platforms. I know also that, for example, Microsoft uses GNU Make to build Windows. So they use the Make to build Windows. It can be non-intuitive in the beginning, so I will go through it step by step. The basic idea is that you have a target that you want to achieve, and you have that target can have dependencies. So something that you require before you can go to the next step. Then you have this, you always have to have a tab. So the target, to achieve the target, you have to do some commands, and those have to be indented. It's also more like Python here, but so the command to achieve the target is indented. So for example, if I want to compress a file like myfile.gc, okay, it depends on myfile.txt. So there must be a text file somewhere so that I can build this. And how do I compress this? So this is a bit there are other ways to do it as well. But so I cut my file. Basically, I just show the contents of the file, and I pass it with a pipe here to gzip that outputs myfile.gc. So that is the recipe from going from so how to achieve this one here. I need to have a file text on my hard drive. This is a recipe to achieve my goal or the target here. So doing this on the command line here, you see I have two files. I have myfile.txt. If I type make here, it executes the recipe. And now you can see I have a GC file again. But the nice thing with make, if you do make again directly in the same directory, it will say, okay, but I don't have to do anything because it's already up to date. So it doesn't do anything it doesn't have to. And that means that it checks that, okay, nothing has changed with myfile.txt. Then I don't have to do anything with myfile.gc as well. But if I do something, so touch changes the modification time of a file. And if I do make again, okay, it makes these, okay, the text file has changed. Then the target is not updated. I have to do the recipe again.
So it checks the last edited time,
yes,
not the content.
No, it doesn't look at the content. So that's why if you have make and your clock is out of skew or something, yeah, you can have problems. Okay. So make sure that you have your clock in your computer set to some NTP in a time server somewhere, because you can get this modification time is in the future or something like that. Yeah. So it doesn't do anything more sophisticated than that. But you can see that you can use this for compiling code. Mm-hmm. So in this case, you have I want to compile source code files to object files. I want to link object files to executables. You have two dependencies here. Object files depends on source files. Executable depends on object files. So this is a very clear case for make. So in this case, I have myprog is my first target. This is I want to build myprog. And myprog depends on an object file, myprog.o. So I will go down and look at the dependencies. So how do I achieve myprog.o? Yeah, it depends on the Fortran 90 source code file. And to get to myprog, I do gfortran-c myprog.f90. Now gfortran provides you a way of doing, you can link everything in a single step. But this is just for illustration. So if you have other files, you do similar things. So now I have an object file here. How do I get my executable? I do gfortran myprog.o, output myprog. Then I get myprog here. So if I look here at ls, I have makefile myprog f90. Make, I first need to build myprog object file. So you can see it first does this rule here, and then it does this rule here. And same thing here, if you touch the myfile, it will rebuild what is required. So in this case here, I have a bit larger example. I have a program that depends on a module and main program, myprog. And I have to compile it. So then I have two rules here. I have myprog.o, builds this one, my module here, builds this one here. And then I have a rule here, I have to link them together like this. So for example, if I have built everything and I just touch my module here, you can see it only rebuilds my module.f90. It doesn't rebuild my prog f90 because it's already up to date. And then it links it together to form a new executable. So if you have in C, you don't have really to depend on the order of compilation, but in Fortran 90, compilation in order is important, especially when we're dealing with modules, because modules are when you compile a module, it generates a file that is used for the compiler to figure out other modules. So you need to make sure that you compile them in the order of the module dependencies. So the module that is used by most modules must be compiled before other modules. But we can have that in our example as well. So in this case, I have three. I have main and truss, two modules, and so in this case here, if I do this, you can see use truss here, count open module file truss mod. So the mod files are what these special files that are used to that contains the type information and stuff like that for a module. And it's not available here because the main module uses truss and it hasn't been built yet. So we need to figure out a way of putting that dependency into the build tree. And we can do that by specifying here that module main depends on my truss O. So that makes sure that this must exist before we can build my main object. So we cannot define this as a dependency of main module. And then if we do that, you can see it first builds module truss and then builds module main. We take a 10-minute break here. Yes, so this is how you can handle module dependencies. You can see here it quickly becomes a lot of code to write, or a lot of file names and stuff like that. So, but there are ways to make it much more easy to read and easy to use. So we can use variables in make, and that can make it easier to configure. You assign variables, just variable name equals the value, and then you can use $sign and variable name to access the variable. And an easy way of using this is, for example, you want to have, you don't have to specify the Fortran compiler millions of times. You do that in one place, and you do define FC, which is a common way of saying Fortran compiler equals to gfortran. You have the compiler flags, you put that in a variable. Executable, you put that in another variable, and then you can see here, I can have a executable here, and you configure it here in the top of the file. And then you give FC here instead of gfortran, the flags. And you can also have a rule here. This is a common rule here. It just doesn't have any dependencies. And if you do make clean, it will do this here. So then it will remove all the mod files, the .o files, and make a clean build directory. This is the first step of kind of making your file more configurable and easy to use. But you can also have more things like internal macros. So the kind of $@ is the target of the current rule executed, name of all the prerequisites, the name of the first prerequisite. Okay, it's hard to read, but it makes things much more easier. So in this case here, you have this one here that points to these two things here. So executable can be built, has dependence on these two objects. $@ here points to both of these. This one points to the current target. So then you get a really simple build rule that is kind of generic. You can also use this one here to point to the first prerequisite here. Then we have some even more powerful, it's called suffix rule, and there you can create rules for kind of how you get from a .o file to or source code to .o file, but for all the source code files. And then you have the same rule and recipes for every suffix in your code. In this case here, you can have a .f90.o. That means how you get from a source code to a O file. You do this rule here, and then you can see here there is also a special variable you can set to define which suffixes are accepted for Fortran, for example. I think this you don't. The last line is just if you have really old make, you can add suffixes here, but most of them are already part of the make system. So now you can have a rule for every source code file. There is also you use wildcards to create lists of files, and you can do path substitutions to modify the names of the files in a list. I think I have to show it in more examples. So for example, I can do a variable that contains all the source code files. So in this case, F90 files :equals to. So if you do wildcards, you need to have :equal instead of equal. And then you have $wildcard star F90. That will list all the files that are Fortran files in your source code directory. You can use path substitution here to, in your Fortran 90 file, replace all the F90s with .o. Then you get a list of all the object files I require. So then I store them in a variable called objects. And then I can do something like this. Executable depends on all objects. And you link it together here by using this simple rule. So now we have a really one-liner to get everything built. So combining this with suffix rules, you can have kind of you get really short make file. Pattern rules similar to suffix rules, and that is also the recommended way to use it in GNU make. It uses the % operator in the same way as wildcard function. So here you can see I have object. This is the thing you do here. So in this case, you have this here is the what they call now pattern rule. So going from star, think it as a star here. So, but any object files that depends on the source code file with the same name, you can create object files like this. Dependencies with the modules here, you can give it on object level. So my module.o depends on my utils.o here. So in this case, you have basically, this is how you get the executable, this is how you compile the source code files. And that's it. It will handle any number of files in your source code directory. It will build them and do all the things that we did before. But now you have a configure generic make file. But I will show you something that's even more easy to use. So this is a completely new, its own language, but it can be hard to master and debug. But we can go one level above make, and then we add a C before make, and then we call CMake. So what is that? CMake is a cross-platform build system. So, and what it does is actually generate build files. So build files can be make files for different compilers or different flavors. And you can also generate project files for Eclipse, Visual Studio, Xcode, so that you can work in a development environment instead. So that is preferably very good on Windows, for example, where a lot of users use the Visual Studio environments. Then you can just open a solution file and then you have your project there. And then you don't have to care about any make or anything, you just build it there. CMake is a language. Many argue that make is also a language, which is a very complicated language, but because of set of rules. But CMake is a complete Turing-complete language. So you express your configuration in another language that you can more easily do more advanced constructs. So this is how you define a CMake file. And the first thing you do is that you always, and this is because there is new versions of CMake, so what you do here, you set this project requires a minimum of version 3.20 of CMake. And then you give it the project name. This is not an executable. This is the name of your project that you want to do. Fortran is not enabled by default, so we have to do enable language Fortran. That thing enables kind of the logic of handling Fortran applications. Then you do, I want to create an executable. It's called simple. It has these source code files. That's it. You don't have to do anything more. It will generate the make files for you on a Linux platform or a Mac. It will generate the project source code files for Visual Studio Code, or Visual Studio in Windows as well. By default, this CMake file must have the file name cmakelist.txt for some reason. I don't know why, but so it will. So if you just type CMake, it will look for that file. So the same thing with make. If you use make, if you have a make file with an uppercase M, that is the first thing make will look at. So you can see here it starts looking at what compilers do we have available, and then it configures everything, and then it writes the build files here in the same directory. So you can see here I get CMake cache. That is just a way that it doesn't have to recompute everything. And you see I get a make file. And then I can just type make, and it will build my Fortran code. The problem is that in this case here, you get a ton of extra files in your build directory that you don't want to have there. So what you want to do is, the recommended way is to create a build directory. So what you do in your source directory, usually what I do is I make the build. I go into my CMake build directory, and I do CMake ... Then it will look outside the build directory and look at the CMake list files, and they will do all the building inside this build directory. So when you're not happy with the build or you want to distribute your code, you just remove the build directory, and that's it. So now you have everything built inside your build instead. Another thing that CMake supports is to have different build versions. So for example, if you want to debug your code, you have a debug version of your code. And you have, if you want to release your code or you want to run it optimized, you have a release version. And you can define that with a CMake build type variable. So you can define that directly on the command line prompt, and that will build an optimized version of your code. And usually what I do, I have two build directories, one build debug, one build release. And I have different builds in each of these directories. Oh, what happens now? Ooh. Yes, so if you want to link with libraries, you do that by specifying an additional line here. Target link libraries. And the first argument is always the target you want to link to. So in this case, I have add executable simple. And I want my simple executable to link with the libraries BLAS and M. And here is something you have to think a bit about because BLAS and M are handled differently depending on the platform. So on a Linux machine, it will be converted to libblas.o or so, libm.something. So, but you give the names of the libraries. And in Windows, it will be converted to blas.lib or m.lib or something. So if you want to have independent routines, you need to make sure that the names are correspond. But I will get that you can handle this by using if statements here as well. And that is the next slide here. So for example, if I have specific things that are different on different platforms, and they probably are, the BLAS library is perhaps called mkl.lib on Windows, you can have if statements. So if I'm on Unix, I should do certain things in my makefile. If I'm on Linux, on Windows, you do different things. And you can do that with if statements, because CMake is a language. So your build process can be defined as a code that you're running. So here you can see here, if I'm on Unix, I add executable multiple, I link with these libraries. If I'm not on Unix, then perhaps I'm on Windows, I use, if I'm on Win32, which is the acronym for Windows, you add different kind of libraries. And if I don't find anything, you can see no supported configuration. So you can express your build needs in very clear syntax here. And if you run this, it will only run one of these. You can also set variables, just like with make, but you use a function called set, and then the variable name, and then the variable contents. And then you use them by dollar and curly brackets to access the variables. You can also create lists by specifying variables with a space between them. And for example, I have set list with A, B, and C. I can do for each I, my list, message I, and that will print out these things. So you can do some very simple loops in the configuration file as well. Actually, many of the new development environments can actually debug CMake files, so you can step through the CMake process as well if you want. You can also add compiler-specific optimization depending on the language you're having. So in this case, I have CMake Fortran, and then you can have compiler flags for release, compiler flags for debug. You can also set the compiler using CMake Fortran compiler. So you can see all the special variables are prefixed with CMake. So you can see here I have I check a get final component name here, and then I have compiler name, and then I check if the compiler is Fortran. I can set the flags to certain things. If it's a iFort for the Intel compiler, I can set other compilation flags. And what other things is cool that you can. So now we have this in make here, but I can also tell the CMake generator to, okay, I want Visual Studio project files. And you use the J command line option to tell the compiler what you want. So in this case here, CMake -J, and then I give it a name here, what kind of output template it should use. And if you look here now, I have a .project, .c project, which are the Eclipse project files. And you can do, if you do CMake on the command, let's see if I can open that. So you have CMake here. If you do a help on CMake, you can see here what generated it supports. So now I'm running on a Ubuntu terminal platform, and you can see the default on Ubuntu is unique make files. But you can see it supports Ninja build files, code blocks, which is development environment Linux. If I run this, I think I have this on Windows as well. Do a normal developer command prompt here. You can see here I can also do all the Visual Studio project files. I can use nmake, which is the standard make file on Windows. Also, if you are working with MSys and MingGV on Windows, you can do make files for those. Ninja files. So you can do a lot of things with that. And I will also show you here so Qt Creator, the development environment, supports makes files by default. And what you can do with that is, if you open a make file, a CMake file in Qt Creator, it will automatically treat it as a project. Let's see if I have my Fortran app here. So you can see here I have a Fortran application here with a CMake lists file. And if I open that CMake list file, you can see here that it spins around a bit here. And now you can see here that it's a project, and you have your source code files here. And if you look here, you can also see the CMake file for that project. So this is so that is natively supported in Qt Creator. So if I run, if you look at Let's see if I have the. Well, let's build it here. You can see also if I check the project here, I can do run CMake. Let's see if I can find it here. You can see here that it actually does the configuration inside Qt Creator here. So Qt Creator there is a default project that you can use, but you can also just work with CMake files directly, and that is regardless of if it's a Fortran project or not. So you can always open a CMake file and use it as a project. And here you can also see some additional features I'm using here. So in this case, to support multiple files in the same directory, I use file glob Fortran files, and then add executable Fortran files here. So then I use a file name here that is the result of this call here, and it also uses CMake include. So if there's something that needs to be included in the same directory, it's automatically added to the configuration. And here I add that I want Fortran here. And here is a special condition. If I'm on Apple, I need to specify which compiler I want to use. So that was what I wanted to talk to you about today.